Okay, section 4.1 was exponential functions and applications. Section 4.2 is a different type of function. They're called logarithmic functions. There is a relationship between exponentials and logarithmics. We will get to that, but for the purposes of what we're doing here at the beginning, it's simply a different type of function that we're going to be working with. Logarithmic functions have the form f of x equals log base a of x. Just a few sort of observational things. I'd like for you to notice that this little a here is a subscript, and the x is right on the same line as log. Every now and then I have people trying to put the a right beside the log and make the exponent somehow on the a. That's not what's going on here. A is a subscript, and the x is right on the same line as the log. A few conditions. The a value has to be positive. I cannot have a subscript that's negative. Also, the a value cannot be the number 1. So having a positive and not equal to 1 is a lot like our exponentials, where we have to have the base positive and not equal to 1, right? Those were the same conditions that we had before, because like I said, there is a connection between these two types of equations. A few things about this. Whoops. The domain is actually going to be 0 to infinity. Okay, all the values that I can put into a log have to be positive, so all the x values. The values that come out of a log are actually all real numbers, so it's negative infinity to infinity. And there are two types of logs that show up in calculators. The first one's called a common log, and the way that it's written is just as though there's not a base there at all, right? You notice there's nothing right here in between sort of as the subscript. When that happens, it is an understood subscript of 10. It's a base 10. Common log, because that's our common base in our number system, right? We're a base 10 number system. The natural log, again, has nothing written down, but notice that it actually says ln. So log natural. So we are not the only way of, the way we do our adjectives and our nouns is backwards of many other languages. If you've studied Spanish, for example, you put the adjective after the noun, right? We put our adjectives in English before the noun. So that's why this is showing up as ln instead of, say, like nl, is because of the language components that are there. So we have ln. This is actually understood, again, to be a log, but the base is e. And it's that same e, approximately 2.718, that we just saw in the last section. Okay, a common log.
So when you're putting
Or, natural log. Yes?
You can put in regular log, and when you put in the base, you can put e, and it'll act as a natural log?
So that's a good question. Your calculator does not have a direct way for you to put in a log that's anything but 10 or e. We will talk about how to manipulate your calculator to allow you to put in, say, log base 3 later on. But right now, the only functions that you have in your calculator is one that says log, which is log base 10, and the one that says natural log, which is log base e. Those are the only operations your calculator has.
Mine, I can put in, on just not the natural log, but just a common log, I can put in.
Yours actually has that capability. That's very unusual that you have a unique calculator then. Most do not.
Mine does.
Yours does too. Very cool. Okay. So that's great. You'll have some manipulations that will be a little bit easier for you than for the other ones. But we're going to actually talk about those calculators which don't have that feature, how you can use your calculator to do that. I don't think it happens in this lesson today, though. I think it's in 4.3. Okay, everybody good so far? We have this new creature. We don't know what to do with it, but we've got it, right? Yeah. Okay, so the first thing that we're going to do is we're going to actually talk about the relationship that we have between exponentials and logarithms. In particular, how we can manipulate one form to get the other. So these equations that are given in log form, and the directions simply ask us to rewrite them as an equivalent exponential equation. So the first thing I'm going to do with you is something that's very visual. I actually am a visual learner. I do things a lot with visuals, and so it makes sense in my mind very much. May or may not with yours in the same way. But what you're going to do is you're going to circle the base 3. Okay, your calculator's not going to help you whether you have the bases or not right now for what we're doing. You're going to circle the 3, and you're going to draw an arrow, curled arrow, all the way around. So I had someone that I was observing teaching once upon a time call that a scorpion tail. So if you've ever seen a scorpion, I think that's a very good description. It very much looks like a scorpion tail. So if you hear me refer to it like that, this is what I'm talking about. We always circle the base, and we always draw the arrow all the way to the other side of the equation, and we land right beside the base itself, next to the log, okay? What this tells us is how to rewrite. We start with the circled piece. That log base 3 is now the base of an exponential. And we follow our tail all the way around. The 4 is what we encounter next. The 4 is our exponent now for our exponential base. We pass across the equal sign and we land on, in this case, an 81. And it is in fact true that 3 to the 4th is 81. That is a true statement. Okay? So this is the equivalent exponential and logarithmic forms of the same statement. Log base 3 of 81 is 4, 3 to the 4th is 81. So it's kind of like back when you were in elementary school, like my daughter, learning fact families, right? You learned that 3 plus 5 is 8, and 5 plus 3 is 8, and 8 minus 5 is 3, and 8 minus 3 is 5. They all go together, right? They're a fact family. This is the same thing. These are in the same family of ideas, okay? We can do the same thing on B, except that on B you'll notice that there's no base written there. So what is our base? It is 10. So there is an understood common base of 10 here that I will put in and circle. And then I'll draw my scorpion tail around. So I start with the base, 10. I cross to the other side of the equal sign. I have an exponent now of z. And it will equal where I land, which is 1,000. Now on A, there's no variables, right? It's just a statement, and it's a true statement. That's good. I mean, on B, this would actually be one where if we needed to know what in the world does z equal, we could do that from this form. It doesn't ask us to do that, so please be sure to follow the directions that are being asked. We're done with this problem. But if we were asked to solve on part B, we could. Do you know what z should equal? Nope, it's not 10. It's 3. 10 cubed is 1,000. Do you guys see that? If I take 10 to the power of 3, it's 10 times 10 times 10, it is 1,000. Yes, Kylie?
When you do the scorpion tail, why does it point to the 1,000 when it has nothing to do with that? It has something to do with the thing on the end. So why wouldn't you point it to like the z?
So I'm following it. It's a directional thing. It's really what it is. So the 10, and then I get the z next, and then I get the 1,000. So it's 10 to the z equals 1,000. It's really giving me direction. The scorpion tail is just a visual imagery that I describe it as, but it's the direction of the change that's being made. Okay, so far so good? Okay, so we were not asked to do this on this problem. Please don't misunderstand. But we're about to be. We're about to be. So on these, we're wanting to go the other direction. We're wanting to change them into exponential form. And we can do the same thing with that directional arrow or that scorpion tail if you wish. You actually start with the base. It's just that it's the base of the exponential now. And you draw your arrow around and you land next to where you started. You're always landing next to where you started. The difference here now is that the base that I circled becomes the base of the log. So I have to put log in and put that base down here, 10. And then following my arrow around right here, the next thing I get to is the W. So the W is beside the log, and it equals where I land, which is a 5. And you could write it like that, or you could simply write it as log W equal 5, because it is the common log. I mentioned that because if you were looking in the back of the book, that's probably what it would do. It would probably give you this form of it, simply because it's a little more condensed, not because it's any more correct. Any questions on that one? Okay. So on B, we circle the base. So whether it's on the left-hand side or the right-hand side of the equation is completely irrelevant. You circle the base, and the base here is B. Okay, if it bothers you for it to be written like this, just switch it around, write b to the k equals z. Do it that way instead. But you always draw the arrow to the other side of the equation. So it's going to go to the other side of the equation and land on the k. So this arrow looks a little funny. It doesn't really look like a scorpion tail anymore. Again, if that bothers you, just use the form over here that I did and draw the base here and then go back around the other way, okay? So the base is b. So this is log base b. The other side of the equation is the z. So log base b of z, and it equals the exponent, which is a k. So some of your questions, you're simply going to be changing forms, one form to the other, back and forth. That's it. That's all you're doing, okay? But we're also going to be using that ability to change the forms to solve things. Now, right now, anyway, logs are not something that you're super familiar with. I mean, even if you've encountered them in a class before now, it's not something that you've encountered as much as you've encountered exponentials. Okay? You've definitely seen more exponentials in your life than you've seen logs. So it's a form that we're more comfortable with working in. So looking at these examples, notice first of all, these are not equations. There is no equal sign, correct? So David and Levi are going to have to be extra careful because your calculator is going to give you great ability to just find me a solution, right? And you can totally use your calculator to find it, like what you're shooting for. But you're still going to have to show work that you understand what it's doing. All right? So what does that mean? Well, it means that we're going to be changing these into exponential forms in always the same way. We're going to start by putting it equal to, and you can choose your favorite letter. I'm going to use x, but if you don't like x, use something different. So every single time we do this, we're going to take the expression and we're going to create an equation that's equal to an unknown quantity, a variable. And we're going to change it just like we did with the scorpion tail in the previous slides. We're going to draw the circle around like so. So this is 2 on the left to the x, which is across the equal sign, and it equals 16. If it's something straightforward enough, and this one might be for you, you might simply know what x is. Kind of like when we did that over here with the 10 to the 3. Some of you knew what it was, some of you thought you did, and then you made a mistake, but you realized it later, right? So this is one you might be able to look at and say, oh, I know that the answer is, does anybody know?
4.
It's 4. You might just look at this and say, oh, I know 2 to the 4 is 16, so the answer x equals 6 is 4 is done, and I'm good, okay? That's great. If you don't, or if it's more complicated, which it will be very quickly, I'll show you in a moment, what you're wanting to do is you're wanting to get the bases on the sides to match. And we talked about this back in section 4.1 last class period. You actually have to take the 16 and figure out what it is as a base 2 object, and it's 2 to the 4th. And then you can see that the exponents would have to equal one another, so x is 4. Now that's probably a little overkill in this particular example, but it might not be on the next one. Okay? So we end up getting x is 4 in some fashion. If you take a look at part B, that rewriting process becomes a little bit more useful. I circle my base, I put equals x. I circle my base and I draw my arrow around. So I have 1/5 to the power of x equals 25. You might be able to manipulate with a little bit of trial and error to find me the value for x here. I get that. But it's probably not something that you look at and you immediately know, like some of you did, that 2 to the 4th was equal to 16. However, 1/5 and 25 both seem to have factors of 5 in some fashion that I could utilize, right? And in particular, I could take the 1/5 and write it as 5 to the negative 1 power. And how could I rewrite 25 with a base of 5? 5 squared. Okay, so again, the goal we're really seeing here is that we want them to say 5 and match on both sides. And we have that, and we're almost ready to do that, to deal with that now. The only other thing to deal with is the fact that I've got an exponent raised to the exponent over here, but we've seen properties of exponent rules before, and what do I do with those exponents? I multiply. So this is a negative x as your exponent, and this is 5 squared on the right. So I ignore the bases, and I set the exponents equal to one another. Negative x is equal to 2, which means x is equal to what? Negative 2. And that is my solution. If you wanted to confirm this with your calculator that x equal negative 2 makes sense, you could go back to the first step that you were working with where it was an exponential form, and you could type in 1/5 into your calculator, and you could raise it to the power of negative 2. And provided there's not a parenthesis issue or something like that, if your answer is correct, it should give you that equals to 25. Okay? C is another one that you might, C and D, that you might actually recognize them before you actually have to set up equal bases on the side. So let's take a look at this. First it equals x. What's my base? It's a 10. So every single time I expect to see the rewritten part. That part is non-negotiable. You're going to draw a scorpion tail around. You don't have to draw it, but you're going to do the rewriting that comes from it either way. 10 to the power of x equals 10. The base is actually already matched. You probably know exactly what x has to be. X has to equal 1.
Logs can equal.
The base of the log can't equal. So down there we have the base of 10. That's the part that can't equal 1. Yeah, good observation. This one, equal x. What's its base? E. So this is an E, right? Log base E. I know it says natural and whatever, but this is log base E. So I'm going to circle my E and draw my arrow. So this is e to the x equals 1. Yeah, so my exponent here would actually be the number 0. So anytime I'm getting my log, it doesn't just have to be ln1. If it said log 1, if it said log base 3, 1, as I work through this, I'm going to get an exponent of 0. That x equals 0 there, because e to the 0, just like any number to the 0 power, is equal to 1. Okay, so I'd like to show you the graphical relationship between exponential graphs and log graphs. Because so far I gave you some domain stuff, I told you what the bases could and couldn't be, those kinds of things. But I'd like to make a graphical comparison so that you can see how this really works. So the first thing I'm going to draw in is I'm going to draw in those exponential graphs that we had back in section 4.1 as a reminder, and I'll label them as such, and I'm going to draw them with yellow. So this one was 1, it crossed at 1. This was the equation, they're using F, so I'll use G. G of x equals a to the x. And then when the a value was between 0 and 1, it looks like this. And this was g of x equal a to the x. So those were the equations that we encountered last time when we looked at the setup of exponentials. Okay, is that like everybody kind of remembering those sets of equations? Okay. Well, here's our graphs for logs. So I'm going to draw them in white, and I'll label them as well. So this is the most obvious one. I'm going to do them one at a time. Do you see how these form symmetry? Can you see how it's a relationship that seems like, oh, look, I see something happening there? So what's actually happening here, and I'll use a dotted line to show it, is that this is a reflection across the line y equal x. That yellow, if it were reflected across my black dotted line, would land right on the white and vice versa. So there's a reflection over the line y equal x. So you notice the symmetry that's happening switches all the x's and the y's. For example, what used to be the y-intercept here at 0, 1 is now an x-intercept at 1, 0. Right? X and y switched places. What used to have a horizontal asymptote of the x-axis now has a vertical asymptote of the y-axis. So my vertical asymptote, the y-axis, is actually x equals 0. Of the two graphs, this one's the easiest one to see. Let me draw the other graph for you. Now, everything that I said before is still true, at least if I've drawn it well, which I certainly haven't. Let's try that again. I like it to be still a little convincing. Well, that's not too bad. We'll go with that. And if I were to draw that line y equal x, it would look something like that. And while it isn't so nice and clean, right, where each piece is on a separate side of the dotted line, can you see the reflection taking place still? That if I fold it up alongside there, the yellow and the white correspond, one piece flips to the other piece, that sort of thing. Everything I just said is still true. My x-intercept is still now 1, 0. And my vertical asymptote is still the vertical line x equals 0, or the y-axis, flipped around from what I had before, which was the x-axis. Not only that, but everything that we learned back in chapter 3 about like reflections of graphs and shifting them left and right and up and down. I know that's blinking, I'm sorry. All of that still holds for log graphs just like it did for quadratics and cubics and exponentials. So as we're taking a look at this next section, what we're going to be doing is we're going to be actually graphing some of those shifts. This one actually doesn't have any shifts in it, but it does give you a base of 8. The base itself talks about how narrow or how wide something is, but it doesn't actually change the sketch that we draw. So what we're drawing here is just simply telling us which of these two graphs we're in. In particular, our base is 8, which means it's bigger than 1. So the graph I'm going to get looks like the first white graph on my screen. So I have a graph that's crossing at 1, 0. It's an increasing graph like this. That's as much of a sketch as I really need to make. Okay. My vertical asymptote. What is my vertical asymptote on this graph? X equals 0. Now, we're going to do my x-intercept I've already plotted. It doesn't actually have a place for me to list that, although I could certainly write it down if I needed to. I've graphed it either way, 1, 0, right? What is my domain as you're taking a look at this graph from everything we've talked about domain so far? It is. I start at the asymptote, which is 0, and my graph continues to the right forever, so it's 0 to infinity. My range, right, climbing the y-axis, what is my range?
All reals.
Yeah, all reals, negative infinity to infinity if we write it in interval notation. Yeah. So far, so good? Okay, let's make a change now. Several changes. Apparently, I was just like real anxious to jump right through all the hoops for you right here on this problem. Okay, there are 3 changes that are going to be made to our problem. Somebody tell me one of them that you see.
Right.
Up 3. Okay, so the 3 at the end is up 3. Over here, I heard somebody tell me about moving something else. Right 2. This one moves it right 2. Where's the other change? Well, it's the negative at the beginning, right? What does that negative at the beginning do? It is a reflection, and it is over the x-axis. It's very interesting because as I reflect over the x-axis, right, it goes top down, bottom up, like that. What actually ends up happening is that the graph looks a lot like the other graph on my screen. So if you compare the 2 white graphs from left to right, they are just reflections over the x-axis, aren't they? Yeah, they actually really are. So we do have that going on. So we're working with all these pieces at the same time. What we actually work with was from the inside out. So the most inside is the right 2. So we'll do the right 2 first, right? The inside with x, things are closest to x. So we're going to shift it right 2 first. So previously, my vertical, my asymptote, I didn't ever draw them in before because they were on the axes. We'll shift over to here. Okay, I got to shift it again. Okay, so there's the new vertical asymptote. It shifted right 2. I also need to have the x-intercept shift right 2, so it'll be actually at that hash mark. Then instead of it going, I should have said, this base 8 is the same from the before, right? The base 8, so the image should look like this one. But then I'm supposed to reflect it over the x-axis. So instead of it going up like this, it's going to need to go down like this. Agreed? That's the basic graph I'm going to be drawing. But this point here is going to shift up how many? 3. 1, 2, 3. So my point will be here instead. Instead of it being an increasing graph, it has to be a decreasing graph because of that reflection. And it looks something like that. You have to have this point plotted. That particular point shows the shift. Left, right, up, and down. This point being plotted is sufficient. If you want to write down what that point is, that would be fine too. It's actually the point 3,3 on this particular graph. We shifted it right 2 and up 3. That ends up being a 3,3. What is my vertical asymptote? Yeah, it's x equal to 2. What's my domain? Good, it's 2 to infinity. And my range? Yeah, it's all reals, or negative infinity to infinity. Yes, Jade. It was right 2 because it was here at 1, 0. And so when we move it from 1 to, it moves to 3. Yes, it wasn't at the origin. That's why we're shifting it 2 to the right. We were already on 1 to the right. Yep, good question. Any other questions? Okay, so the next set of questions are kind of like these, where I'm utilizing the ability to shift between forms in order to solve things. But the difference is that these actually start out looking like equations. So this is sort of a combination of the rewrite pieces that we did at the very beginning and the put things equal to 0 or put things equal to x and then solve them, right, that we did in the middle. And so we're going to actually combine those two ideas together, and we're going to use our scorpion tail as we do this. So we will start by circling my base and drawing our arrow around. So 4 is my first value. Then what? Yeah, the exponent is 1/3. Good. And then equals x. Okay, is that okay on the rewrite step? What in the world does it mean to have an exponent of 1/3? It's a cube root. Very good. So as we're thinking about this, we can rewrite this in a much more familiar form, cube root. That might have been the ability to simplify. Unfortunately, the cube root of 4 doesn't simplify. But let's say it had been an 8. If it had been an 8, could I have simplified? Yeah, I could have. So I need to rewrite it in order to recognize that fact. But there's nothing else I can do at this point, so the problem is over. X is equal to the cube root of 4. Okay, so if on part B, I had had something on both sides that was able to be written as base 5s, that's what I would want to do. But 12 cannot be written as a base 5, right? Yeah, no, it's not going to work. It's not a power of 5. So I don't have the ability to use what I did back in section 4.1 and rewrite this and solve it within the exponential form that it's given, which means I need to change it into log form in order to work with it. So I circle the base and I draw my tail around. It was an exponential, now it will be a log. What do I do next?
Log base 5.
Mm-hmm.
12.
Perfect. Okay, is everybody good? David's got that perfect. Sometimes I think it's a little harder to put it back in log form than to go into exponential form. That was good. All right, so that's great. The reason that this is beneficial, outside of the fact that I don't have the ability to get the base 5s on both sides, is that previously I had the exponent, I should say I had the x embedded in the exponent, right? And now the exponent being down on the baseline actually has my x able to be solved for. That's beneficial to me, okay? So I need to solve for my x. So what can I do to get the x alone? Right now it's 3 minus x on the right-hand side. Okay, we can subtract 3. Now you need to remember that that 3 does not have the ability to combine with the 5 or the 12. There's nothing that's combinable, if you will. That's terrible English, but we're going to say it anyway. Over here, this is log base 5 of 12 minus 3. If it helps you to keep them separated, put the log base 5 of 12 in parentheses to remind you of that fact. You cannot combine that 12 and 3. This is equal to negative x. Now what? Divide or multiply by a negative 1, right. And so everything changes signs. I now have a negative log base 5 of 12. And I have a positive 3. And it equals x. Again, if it helps you to put that in parentheses, go for it. Another possibility is you could put the 3 at the beginning if it helps you. Move this 3 to the front. So you could actually write it as 3 minus the log base 5 of 12 to separate them, if that's, more comfortable looking. It's not right or wrong, it's just a different option. But what's not an option is combining the 3 and the 12. That probably looks to you like, well, did you really solve anything? And the answer is yes. It just doesn't have a numerical form you're comfortable with. How do I know it's solved? Well, I know it's solved because everything over here is a number. Okay, log is an operation. It's kind of like having a square root. Okay, you can have a square root inside of a problem. You can have a log inside of a problem. But everything else is numbers. So this is, in fact, the solution. It's just not in an approximated decimal form. We'll learn how to do that later, just it's not this lesson.
So you can do it in either form, like the plus 3 or the 3 minus the log?
Sure, absolutely. Okay, let's try another one. Okay, somebody guide me through what I'm going to do first. Circle the x. Thank you, Tori. What's next? Good. Awesome. Everybody good with that? The rewriting step looks a little funny because all the fractions, but it's all in the same pieces, same places, all good stuff. All right, what does x to the 4/3 mean? Awesome. The cube root of x to the 4th. Okay, our goal is to solve for x, right? The last time we had a cube root, it was actually a number underneath it, cube root of 4. Here it's a variable. I need to solve for that variable. So this cube root can be eliminated by doing a cube. How can I eliminate this 4 here? What would I do if I had this simplified different, something different? It just said x squared equals 16. What would I do to eliminate the square? You'd square root. What would you do to eliminate a 4th power? 4th root. Now I know that's not exactly my problem, but it does have the same form. There is a power of 4 on that x. So I'll be cubing to get rid of the cube root, and I'll be 4th rooting to get rid of the 4. You can do that in whatever order you wish. If you'd like to cube first, you can, but I'm not going to. And the reason I'm not is because it actually makes things bigger, and I'd like to make them smaller. So take a look at this. If I take this, and instead of writing it as the cube root of x to the 4th like this, and I put to the 4th out here, which is equivalent, it's exactly the same thing, it just looks a little different. Then I'm going to take my 4th root first. And I know notationally that looks really ugly, but they cancel. And I like that because the 4th root of 1/16 is easy. Do you guys know what the 4th root of 1/16 is? Well, the top's 1. I'll give you that one. Yeah, the 16, when you take the 4th root, is a 2. So at this point, my problem actually made the 1/16 a smaller number, whereas if I'd cubed it first, it wouldn't be wrong, but I would have had to take 16 times 16 times 16 when I've gotten something very large. So here I made it smaller first, and then I can cube it to make, or to solve for the cube root, and it will make it a little bit bigger. So on the left-hand side again, the cube root and the cube cancel. What is 1/2 to the 3rd power? 1/8. And you get the same thing if you cube it first and then 4th root it second. It's fine. Okay, D is the most unique from what we've done so far. What makes D look different than the other three that we just did? There's a log on both sides. And do you know what the cool thing is about a log on both sides? They don't cancel, but it's just about as good. They just get ignored. Yeah. So do you remember when we were doing the powers where we were getting, actually I had one here, so let's go back and grab it. Here, where I had 2 to the x and 2 to the 4th, and I just get to ignore the base 2's because they match. Remember that? I didn't cancel them, right? They're still there. I just know that they're equal, so I don't have to consider them any longer. They're already there. Same thing over here. When I have a log on both sides, I get to ignore it. And I get to only work with what the insides equal. So I get to only look at the inner pieces, and I get to ignore the logs because they match. 2x equals 24 minus x squared. We've seen problems like that before. What do we have to do to solve a problem like that? Yeah, get them all on one side and factor. I'm gonna move my x squared and my 24 because then my x squared will be positive, and my minus the 24. So I have x squared, putting them in order. Then I have a 2x and minus 24. You can use the AC method if you'd like. Trial and error works pretty nicely because that first coefficient is a 1. So I'm going to use trial and error. I have x and x. What does the sign at the back tell me? Signs are different. One's positive, one's negative. I need two numbers that multiply 24, and their difference is positive 6 and negative 4. Their difference is 2, right? Okay, so check it in the middle. This is negative 4x, positive 6x. Does that give me positive 2x? It does. Cool. Then what? Yep, set each one equal to 0. X minus 4 equals 0. X plus 6 equals 0. So x equals 4 and negative 6. Now here's a catchy thing, or a tricky thing that we have to make sure we're paying attention to. Do you know how when we work with radicals and we solved with radicals, we had to make sure that the answer that we got actually worked back inside the radical because things inside radicals can't be negative? Do you remember that? Yeah, we have the exact same problem going on here. The items inside of the logs, because the domain on a log graph has to be only positive values, means that anything that goes inside of a log also has to be a positive value. Hence, negative 6 doesn't work. Because if I put negative 6 in here, 2 times negative 6 gives me negative 12. And I can't have negative 12 inside of a log. Okay? I do want to make sure that 4 actually works. It works on the left, the one that I circled. Does it work on the right? So 24 minus 4 squared. Will that be a positive number? It will. So I'm okay with the number 4. I'm not okay with the number negative 6. So this one is a solution. This one gets marked out. Do you remember what we called them when we marked out solutions that don't really work? Well, if they both didn't work, we would say there's no solution. We called it extraneous. Do you guys remember that word? This is not a big deal if you don't, but it's an extraneous solution. It's a solution that sort of comes out as a part of the solving process that doesn't actually work in the particular problem. So our only solution to this problem is x equals 4. Any questions on that? All right.